Good morning, everyone. Welcome back. I hope you had a very nice holiday and that it was restful and gave you enough sort of energy to help you make it through the rest of this quarter. I know the pace of this course and generally the quarter system has been quite fast overall, so hopefully you're prepared to make it through the last little bit of this course. So, speaking of the last little bit of this course, the third test is going to be on Monday, January 18th. So, that is 2 weeks from today. So, this test is going to cover sets and functions. So, this week we're talking about sets and functions. Next week we're going to be talking about more stuff with functions. As you'll see, there is a lot to say about functions. And then at the end of that week, at the start of the next week, we'll have the test that covers all of that material. And then after that test, well, this will be the Monday of week 6. So then we'll be talking about cardinalities of infinite sets. So we'll be talking about sizes of infinity and how that sort of puts together a lot of the pieces that we've been talking about so far. And then it'll be week 7. In week 7, we have the final, and classes end on Wednesday. So basically, week 7 is going to be one day. So that sort of gives you the plan for the rest of the quarter, semester, or whatever you want to call it. Tomorrow, there is a faculty meeting during my office hours, rudely. So I'm going to just move my office hours. And so I'm just going to say I'm going to be around in the afternoon tomorrow, aside from a math department meeting. So if you want to meet with me tomorrow, you can email me and we can work out a time. Otherwise, my regular office hours will continue after that, so you should have lots of time to ask me questions if you have them. As I sent you in an email, today we're going to talk about the videos that pertain to sets, particularly the Cartesian product and the power set are our new friends and tools that we'll be using a lot for the rest of the semester. On Wednesday, when we meet, we're going to talk about the rest of stuff about functions that I posted in the week 4 videos. So that will take us through the end of the homework that's due for week 4. But especially given the looming test and given the amount of content that is going to be present in week 5, I'm going to start dipping just a little bit into week 5 stuff on Friday. So before Friday, I want you to have watched just the first video that I've posted on week 5. It's already there about one-to-one functions, so that you are nice and prepared for the rest of week 5, and so that you can start absorbing all of the material that you need for the test. Okay. So this test is just about functions. However, you will be pleased or displeased to learn that most everything involving functions we're going to do is going to require proofs, so you're going to get to do all of the proof methods that we've talked about: direct proof, proof by contrapositive, we'll do some for every there exists proofs, and so on and so forth. So all of the various tools that came to a head on test 2 will be necessary in order to do the things with functions on test 3. And then following that, again, I said we'll talk about cardinality a little bit, but then we'll have the final. And the final, I should mention, is cumulative. However, the vast majority of the content of the final will come from test 3 and before. So I'll tell you closer to the final, because I haven't written the final yet. I'm not that far ahead. But I'll tell you closer to the final exactly what I'm covering that is after test 3. But the vast majority of the final is just going to be asking you if you've mastered the material from test 1 through test 3, because that is the material that you're going to need in future classes after this one. Okay. Are there any questions about any of that? Okay, so let me start by going over your questions. And then from there, we can dive into some more examples just so you can practice the various kinds of skills that are going to show up from the set section. Okay. So first of all, people asked about 2C from the test, so let's start with 2C from the test. By the way, you should definitely make sure you could do every question you got wrong on the test. So if there's something from the test that you don't understand, you should definitely make sure. So I definitely appreciate people asking about test questions. For every x wheels. Okay, so here's what we want to prove. We want to prove that for every real number I can choose, it's possible for me to choose a positive number and a negative number whose sum is that real number. And I want to remind you that we sort of have these stacked quantifiers. So the thing I need to show for each x is this statement that there exists an a and a b such that x equals a plus b. Okay. And so remember that we prove there exist statements usually by giving an example. So we're going to prove this bracketed part by example. But please note the bracketed part is inside a for every quantifier. And so as a result, I'm not going to be able to give one example and call this statement prove it. I'm in fact going to need to give an example for each x. Okay. Or in other words, the example we're going to give has to depend on x. So in other words, if I just say, well, 7 is equal to 9 plus negative 2, this is not a proof of the claim. And this is not enough, again, because it only works for x equals 7. And I need this to work not just for x equals 7, but for every x. There are a great many different ways to prove this. I realize my camera's getting out of focus. So the way I had in mind was to do it by cases. But we can certainly do it in a bunch of different ways. But I'll show you my by cases proof, and if you like, you can look for other ways that avoid cases. Okay, so our proof has to start with supposing that x is a real number. I don't get to dictate anything about x. Okay, and my first case here will be that x is positive. And so when x is positive, I claim we can take a to be x plus 1 and b to be minus 1, okay, then definitely a is in R plus, because I took a positive number and added 1 to it. B is in R minus, because it's literally -1, so it's just definitely negative. And a plus b equals x. Okay. And so that finishes this case. And this is the structure of a for every there exists proof. I'm choosing an arbitrary x, and then I'm showing that it is possible to write down an example. In this case, that example is a equals x plus 1 and b equals minus 1 that meet the requirements. Based on this example, you can probably guess what I'm going to do for the next one. But for x is less than 0, sorry, I'm going to let a equal x minus 1. Sorry. I'm going to let a equal plus 1 and b equal x minus 1. Then, lo and behold, a is in R plus. B is certainly negative because I took a negative number and subtracted 1. And a plus b is definitely x. Okay. And just so that I wouldn't have to worry about what exactly happened when x was 0, I could have snuck x equals 0 into one of these previous cases, but just to be safe, let's just do x equals 0 separately, in which case then I can take a equal 1, b equal minus 1, and then a is in R plus, b is in R minus, and a plus b is 0, and then we're done. Okay, questions about that? I do think this for every there exists structure is probably the hardest to wrap your head around, but it's very important to do it soon, because when we're talking about onto functions next week, it's going to turn out that we're going to be writing down basically a whole homework assignment's worth of for every there exists proofs. So it's important to internalize this structure. Someone asked about talking about infinity and dealing with infinite sets and these kinds of things. I'm going to do some examples of infinite sets later, but I do want to point out that there's sort of like at least 2 different flavors of infinity. Okay. And in this course, we're only dealing with one of these flavors, but I want to point out that they're actually a little bit different. So in the calculus flavor of infinity, which is the one we're not dealing with in this course, is a name for sort of what happens if you keep going this far in the real number line. So this is sort of like the pot of gold at the end of the rainbow or whatever. Basically, this is just a stand-in that you use as part of talking about what happens when you go infinitely far in this direction, or if you just keep going towards the positive side of the real line forever. So this is sort of the end, in quotes, of the real line for limits. But the clever part of calculus, or one of the many clever parts of calculus, is that you get to use this as a concept without ever having to actually deal with it as a real thing. So you never plug infinity into anything. You never need to treat infinity as though it actually exists. Infinity is just a convenient stand-in for what happens when you go all the way sort of in this direction. On the other hand, we have the cardinality flavor. So in the cardinality flavor, we have these numbers, and so we have things like, well, the size of the set 1 is 1, the size of the set 2, 3 is 2, and so on down the line. But then we get to some sets like the positive integers, and we want to talk about their size, or the size of the real numbers, and we're sort of stuck because, well, they're not the size of these is not a positive integer. And so we've just been writing infinity so far. Okay, but preview, the thing we have yet to do is we need to resolve that these are actually not quite the same infinity. Okay, and I have not been very specific at all yet about what exactly that means, so I'm just going to put it in quotes, but that's what we're going to talk about. Is that really, as far as we've considered so far in our lives, there are really two kinds of infinite sets. And so there's actually two infinities that we'll end up talking about in terms of sizes of sets, and these, in fact, are both of them. Okay. And these conceptually lie in a completely different universe than the calculus flavor of infinity, where the calculus flavor of infinity, in some sense, doesn't really exist. But the size of the set of positive integers exists in whatever sense you want to talk about any concept like this existing. And so we'll talk about it and we'll disambiguate all of these things. And it's, in fact, going to be strictly necessary to have a really strong grasp on functions to understand what I mean when I say that these two infinities aren't the same. Okay. Okay, so someone asks, when you're talking about power sets, or in general, what is the difference between the set 2 and the set 2? And I think it's actually clearer if instead of this, I talk about the difference between the set 1, 2 and the set 1, 2. And so what's the difference here? The difference is, among other things, what are the cardinalities of these? So what's the cardinality of the set on the left, and what's the cardinality of the set on the right? You can write both in the chat as a list. A lot of people are saying this set has size 2 and this set has size 1, and you're completely right. So this set has size 2. It has 2 different elements, whereas this set only has 1 element. And so the difference between these is really what the elements are. Namely, here the elements are 1 and 2. Those are both elements of this set, whereas over here, the only element is the set 1, 2. Okay. Now that gets a little weirder when you go back to the example that was originally asked about, because for the first set, well, 2 is an element of the set 2. Okay. 2 is not an element of the set 2, but the set 2 is an element of the set 2, which is a little bit weird. But in fact, what you could say is 2 is an element of this element of the set 2. Although I feel like writing things like this down probably has the opposite of the desired effect. Namely, I think this probably makes it less clear what's going on rather than more clear. Someone asks if it's possible to use the definition of power sets to prove that the intersection of the power set of A and the power set of B is always none-empty. I would argue that's basically what we did when I proved it in the video, which was to say that by definition, the empty set is a subset of both A and B, so it is an element of the power set of A and the power set of B, and so it's in the intersection, and so the intersection's not empty. But it's possible that you have something different in mind, in which case you're welcome to ask, and I can talk about it in more detail. Okay. But it's important just to reiterate that if the empty set is an element of a set, then that set is not empty. And writing these kinds of things takes a bit of getting used to, because thinking about what it needs for the empty set to be an element of something takes a bit of time to sort of wrap your head around, because just like we were just talking about with the set 2 and the set 2 and the set 2 and so on, the empty set being an element is very different than the empty set being a subset. In fact, what does it tell us about a set if I tell you that the empty set is a subset of it? I don't think, actually, that we can conclude that it's a power set. I think that's the right answer. Saying that the empty set is a subset of a set tells you absolutely nothing. Because the empty set is a subset of every set. Okay. On the other hand, saying that the empty set is an element tells us something very specific about the set, because most sets we've written down do not have any sets as elements, much less have the empty set as an element. Or, sorry, have the empty set as an element. Okay, someone asks about what does the Cartesian product of two power sets look like? And we'll do some examples with this later, but let's just look at the power set of z plus cross the power set of z plus. Okay. And ask ourselves, what does an element of this look like? In fact, go ahead and just write one element of this set in the chat. I think 4, 9 is actually an element of z plus cross z plus. So I don't think it's an element of the power set of z plus cross the power set of z plus. But, right, so if you took something like that, here the set 2 is a subset of z plus, and the set 3 is a subset of z plus, so this is an element of this. Or if you want to make a little more clear what's going on, you can take something like this from the chat, where you have a set in each slot. And, of course, you're also allowed that, because the empty set is an element of the power set. And you're also even allowed this, as weird as that looks, because z plus is a set, and it's definitely a subset of itself. So, how do we know whether the elements of something are sets or ordered pairs? Okay. And so the answer is, if it's a Cartesian product, then the elements are always going to be ordered pairs. So in this case, this is a Cartesian product of something and something else. And so the elements of blank Cartesian product blank, whatever sets you put here and here, elements are always ordered pairs. Whereas, if you take the power set of anything, the elements are always sets. Okay. And where this gets confusing, I think, is when you have either this, where you have the power set, where you have a power set cross a power set, but that's still just putting something in the blanks here. Namely, you're putting the power set of z plus and the power set of z plus in the blanks. So that's why they still end up being ordered pairs. Or if you have a power set of something complicated, like a Cartesian product, then you might be tempted to think, oh, it looks like this, but it's not quite the same thing. If I have this, for example, this is the second type of thing. This has elements that are sets. Okay, I'm about to talk about questions from the homework, but before I talk about questions from the homework, are there any more general questions about power sets, Cartesian products, all of these new set things that we've talked about, or anything you don't think I addressed to your satisfaction out of this? Okay, so the first question from the homework I actually want to talk about is actually someone asked about 49C. Which goes all the way back to before the break, so very good memory. So this involved this tangled web of definitions. So if you look back, there's this whole business of a P3 set. This is a subset of Z plus such that there exist X, Y, and Z. I guess I should say a subset S of Z plus in S such that X plus Y plus Z is prime. Okay. So, for example, if I took the set 1, 2, 3, 4, this is P3 because 2 plus 2 plus 3 is 7, which is prime. And then we have this definition of the core of a P3 set. So this is sort of a nested definition. Okay, and this is defined to be the set of little s in S such that big S minus the set little s is not a P3 set. And so if I took, for example, the core of my previous example, 2, 3, 4, then in order to figure out what was in the core, I'd have to write down what I get when I remove each element. So when I remove 1, I get 2, 3, 4. When I remove 2, I get 1, 3, 4. When I remove 3, I get 1, 2, 4. And when I remove 4, I get 1, 2, 3. Okay. And so the elements in the core are those of these which are not P3 sets. So if I were to circle all of these that were P3 sets, how many of them would I circle? That's right. All 4 of these are P3 sets. Okay. Now, I can give one explanation for why all of these are P3 sets, which is that 1 plus 1 plus 1 is 3. And so, in fact, as soon as 1 is an element of a set, it's automatically a P3 set. But this is also a P3 set, and it's a P3 set because 2 plus 2 plus 3 is 7, which is the explanation I gave before. Okay. And so by this definition, then, what is the core of this set? This is the empty set. That's exactly right. This core is supposed to be the set of elements of S that if I remove, I make S not a P3 set anymore, but there are none of those. Because as we said, all three of these things are still P3 sets. That was all by way of reminding you what these definitions were so that I can say what 49C actually asks. So 49C actually asks, is there a P3 set whose core is infinite? And this is an example where, by using the word infinite, I made the question really scary. Whereas if the question had actually said what's actually true, I think it would have been more clear what to do, which is actually, here's the true statement. So the answer is no, but I'm going to prove something a lot stronger. The true statement is actually that if S is a P3 set, then the core of S always has size less than or equal to 3. So I'm going to show you that not only is it not possible for there to be an infinite core, that in fact the core can never have more than 3 elements in it. And here's the proof of that fact. So let's suppose S is P3. Okay, what does that mean? Well, by definition, that means that there exist these x, y, z. In S, such that x plus y plus z is prime. Okay, now claim if, let's pick our favorite letter A, I'll be boring, is an element of S minus xyz, then S minus A is a P3 set. And the proof here is that x, y, z are elements of S minus A. And we already know x plus y plus z is prime. Okay, so that proves the claim. And so thus, if A is an element of S minus xyz, I've in fact just shown you that A is not in the core. But that actually leaves only 3 things that could be in the core, namely x, y, and z. Uh-oh, my camera seems to have frozen. Unfreeze camera. Let's see. There we go. You can still hear me, right? Excellent. And so, since the core of S is a subset of XYZ, that tells me that the core of S always has 0, 1, 2, or 3 elements. Okay. In particular, definitely not infinitely many elements. Any questions about that? I know that was probably the weirdest question, or one of the weirdest questions from that homework. Okay, so there are a couple questions from the homework that I want to talk about based on requests. So there are a couple parts of 53 that people wanted to talk about. A couple of people want to talk about 55. And I think, did I also get a request? Did I imagine? Oh, yes, and 56 someone wanted to talk about. Okay. Are there any other questions from the homework that people want to talk about that are not on this list? Oh, I guess there aren't really other questions on the homework. This is almost every question because the homework for Wednesday is just 53, 54, 55, and 56. Okay, so for 53, some people asked about F and G. So for 53, F and G, these things both involve the power set of, and then this confused people. Sorry, that. And I think people were confused because I think they sort of wanted this to be this. But it wasn't, and then they thought they might be missing something. And so this 0, 1, this is the closed interval. So this is all the real numbers between 0 and 1, including 0 and 1. So for 53, F and G, that's what's going on. Okay, for 53C, someone asks about, this is the union as I goes from 3 to 5 of the set of 2 to the I and 2 to the I plus 1. So this is the thing where you need to treat it as being like a big sigma that you'd use for a summation in order to calculate this, but just take the union of all of those sets. The thing that I might note is that because I didn't put a display style in it, which was my fault, it wrote it like this, whereas if I was writing it by hand, or if I'd put a display style, it would have written it like that. So those mean the same thing. Someone asks, what does the power set of a continuous interval look like? And the answer is it's enormous. Because there's definitely infinitely many elements inside this interval, and so when I go to write down subsets, there's lots and lots and lots of subsets to choose from inside the interval 0, 1. In fact, when I said earlier there's sort of like two sizes of infinite set that you encounter on a day-to-day basis, in fact, it will turn out, and we'll prove this later, that actually the power set of a closed interval is actually an even bigger size. So that's sort of a third size of infinity. So it's bigger than any set you're used to considering by quite a bit. Because it contains, for example, like all the numbers between 0 and 1 that don't have 7 in their decimal expansion. Just all sorts of random stuff. Every possible subset, and it turns out there's lots of possible subsets of the interval 0, 1. I'll note, though, that in the context of this particular question, the fact that this set is huge actually makes it easier because you only have to list 3 elements. And so if there are, for example, a whole bunch of elements, then there's more elements to choose from. A few people ask for a hint on 55. My hint on 55 is to first think about what the power set of O union the power set of E is. Okay, so do it a piece at a time. Okay, so someone asks, when I say explaining in words what this thing is in 56, what do I really mean? So when I say describe it in words, what I mean is tell me what kinds of things are in it. They're ordered pairs of what? And in this case, they'd be ordered pairs of subsets of S. But they're not just any old pairs of ordered subsets of S. It's ordered pairs of subsets of S with this particular property. And so you should be able to write down ultimately a sentence that's pretty lucid and understandable that says what it means to be an element of this thing that's called xi of S in the homework. Okay, I have some additional questions that I have queued up to ask you. But before I get to those questions, are there any additional questions from other things that people want to ask? So there were a lot of questions about proving sets were infinite and all of this kind of thing. So I'm going to just give you a few examples of that, and I'll give you some time to work on them. So the exercise here is really twofold with these pieces. It is to think about what the set notation means and dissect it, and then to remember what our key is when we're proving things are infinite. Namely, remember a set S is infinite if and only if there is a non-repeating, non-terminating list of elements of S. Okay, so if you want to prove a set is infinite, you can do so by producing a non-repeating, non-terminating list of elements of it. Sorry, I said that like there was a second part, but that's it for this. So if you want to prove these two sets are infinite, the best way to do it is to prove that there's a non-repeating, non-terminating list of elements of it by writing one down. Okay. I'll give you, say, 8 minutes to think about these, so we can pick back up at noon and we'll talk about these questions, and then I'll have a few more questions for you to think about after that. All right, welcome back, everyone. Oh, I never put the light back on. I don't know that it makes a huge difference, but let's talk about these questions. So, first of all, for each of these sets in this first part, let's write down just a description of what the sorts of things in these sets are. So, in the first one, this is the set of subsets of Z plus with two elements. So remember, when I put absolute value bars like this around a set, I no longer mean absolute value, I mean cardinality of. Okay. And so 1, this is the set of two element subsets of the positive integers. So then I just need to write you down a none-terminating, none-repeating list of elements of the set of two element subsets of Z plus. And I think we can do that. So 1, 2, 2, 3, 3, 4, and so on, is a none-terminating, none-repeating list of elements of this set. Are we happy with that? I think the pattern here is clear enough that I don't think you need to write down that the nth term of this is n plus 1, but it would not be wrong to, and certainly it would be a more complete proof if you specifically wrote down that, hey, that's what I'm imagining the nth term is here. So I guess I wouldn't complain if you didn't, because I think there's a clear pattern in the way I wrote this. But, I mean, when in doubt, write more, I would say, is the general philosophy. Any other questions about this example? For this second one, this is the set of ordered pairs of x and y that satisfy x squared plus y equals 1. Which might be better known as the graph of y equals 1 minus x squared. I mentioned this in the videos, but I just want to reiterate, when you're talking about subsets of R cross R, it's very natural to think of them as graphs, although not necessarily graphs of functions. But you can think of them as collections of dots that often will have shapes. So for example, in this case, if you looked at the subset I described in part 2, it would look exactly like this, sitting inside of R2 in our usual fashion. And so if we want to write down a list of elements of it, I would write it down as 1, 0, 2 minus 3, 3 minus 8, 4 minus 15, ... And here, actually, just to be crystal clear, I would actually write down that my nth term here is n, comma, 1 minus n squared, because you might not get it if I did not write that. This is an infinite list of elements of the set. Or sorry, I should say none-repeating, none-terminating list. Of the set. Okay, and so that shows me that this set is infinite. Okay. Now note, this is very far from listing all of the elements, because actually I started by listing this element first, and then the next one I listed was some way along here, and then the next one was some way along here, and so on. So there's, well, infinitely many red points for every blue point, but that's perfectly fine. All we need to do to show that a set is infinite is provide a none-repeating, none-terminating list of elements. If someone was really picky and they asked, how do you know that this list is none-repeating, what would you tell them? How do I know that no two elements of this list happen to accidentally be the same? Exactly what I would say. The first coordinate of each pair is increasing, so it can't repeat, right? It goes 1, 2, 3, 4, and so on. And so because this first coordinate is increasing, it can't be that any two of these are equal, because for them to be equal, it would have to be the case that their x coordinates were the same, and that never happens. All right. Questions about showing these kinds of sets are infinite? Okay, let's go on, and let's prove that the union of two sets is infinite if and only if one of the sets is infinite, or both of the sets are infinite. Remember, our ors are always inclusive. Okay. So let's first prove this direction, which is that if A or B is infinite, then A union B is infinite. Okay. And I'll note, this should be a very plausible claim, right? That if I take a union of two sets, one of which is already infinite, that I'm definitely going to get something infinite. Okay. But here's how I would do it. So one way to do this is to do proof by cases, where I do one case where A is infinite and one case where B is infinite, and then I show this. Or even this would be a perfectly appropriate time to say, without loss of generality, A is infinite, and then do that. That would also work. But since A or B is infinite, I'll just write it this way. It is possible to write a non-repeating non-terminating list of elements either of A or of B. If you can do both, pick one. So do so, and we'll call it x1, x2, x3, so on forever. Okay. So in other words, if A is infinite, this is a non-repeating, non-terminating list of elements of A. If B is infinite, this is a non-repeating, non-terminating list of elements of B. But now I need to make one observation about this list to finish the proof. And what observation do I need to make about this list in order to finish the proof of this direction? Right. This list is also in A union B. So A union B is infinite. Okay, so next we have the forward direction, which is we need to prove this statement that if A union B is infinite, then A is infinite or B is infinite. Okay. So I think it's much easier to prove the contrapositive. You certainly can prove this directly, but I think the contrapositive is probably nicer. So in this case, the contrapositive is if A and B are finite, then A union B is finite. Okay. And somehow I think this statement is much less mysterious than the previous one. Okay. So let's suppose A and B are finite. And let's say the size of A, let's call it M. And the size of B minus A, let's call it N. then we can write out A is x1 up to xm, and B minus A as y1 through yn. Thus, if I want to write out A union B, then I could do that as x1 up to xm, y1 through yn. And so what does that tell us? That tells us that A union B has size m plus n. Okay, question for the audience. Why did I do the size of B minus A instead of the size of B? Exactly. I don't know if A and B have any intersection. And so if I just wrote the list of elements of A followed by the list of elements of B, I wouldn't know if there were any repeats. And so then when I want to try and count the number of elements in A union B, I'd have to think about it more carefully to argue that in fact this thing was definitely finite. But here I didn't have to think about it because I could just write down the number of elements in B minus A and then just write this out. And so then the union, in fact, gives me A and B because I only counted the elements in A union B each once. Okay, so there were a lot of questions about infinity and proving things are infinite or not infinite or whatever. I hope this helps. If you have more questions about it, definitely let me know. I'm happy to talk about this more. And as I sort of alluded to, it's what we're going to be talking about week 6 for the majority of week 6, probably for all of week 6. Okay, here's a shorter question. So I'll give you less time to think about this, but I'll give you some time to look at this. What is this set? That is my question. So list or describe or whatever, find all of the elements of this set. I'll give you a couple minutes to look at this, and then I think we'll be in good shape. Okay, so let's talk about this set. So how many elements does this set have? I agree. I think it has 1 as well. So let's figure out what that 1 is. So first of all, let's dissect this statement. What does it mean for two ordered pairs to be equal? It means their first term is the same and their second term is the same. So what is it we want? We want to know when x minus 2y is 1 and 2x minus y is 5. And this is really a system of equations for us to solve. Okay. So let's do that. So I'll solve the first line, which will give me x equals 1 plus 2y. And then I'll plug that into the second line, which will give me 2 times 1 plus 2y minus y equals 5. So that'll be 2 plus 4y minus y equals 5. So that will give me 3y is equal to 3. So y is 1. And if y is 1, because x is 1 plus 2y, x is 3. Okay. So I want to think through the logic of what it is we've just proven. Because we're not done yet. What we've just proven is that if xy is an element of this set, then xy is 3, 1. I'm going to give this set a name. I'm going to call it capital A, so I don't have to recopy it. Okay, that is what we just proved. Because when we wrote down these equations and then solved them, we started with the equations we wanted and just assumed they basically were true and then figured out what that told us about x and y. So in our current state of knowledge, we actually only know A up to 2 possibilities. One possibility is that A is the set 3, 1. Or, what's the other possibility? What, based on this if-then statement, could A also be? So what we proved, again to reiterate, is that all the elements of the set A are equal to the ordered pair 3, 1. But annoyingly, there are 2 sets with that property. Namely, there's the set which just has 3, 1 in it, But there's another annoying set that also has that property. Namely, the empty set also has that property. And so what am I left to do? I'm left to decide which is it. And fortunately, it's not actually hard to decide which it is. All I have to do is plug this in and see if it's actually in A or not. So namely, I now just have to ask the question, is 3, 1 in A? So I go back up here and I say, okay, so 3 minus 2 times 1, comma, 6 minus 2. That will work out to be 6 minus 1. That will work out to be 1, 5. Aha. So it is. Okay, and so as soon as I do that check, I now know A is not the empty set, and so A really is this set. And then we're done. Just to convince you that this difference really does matter, let's look at something like this. Okay. So if you were to solve this, you'd basically just solve the equation log of x minus 1 plus log of x plus 1 is equal to 1. So then in order to do this, I'm going to rewrite this as the log of x squared minus 1 is equal to 1. Oh, I realized this is not going to work the way I wanted. Anyway, I'll show you what can go wrong. So that tells me that x squared minus 1 is equal to e. So x is plus or minus the square root of e plus 1. Okay. Because I made up this example off the fly, I don't think this is going to work out the way I wanted to. So these are two solutions, but they're only possible solutions. These are not definitely solutions. Because what can go wrong is it can turn out that when you plug these back into the original equation, it turns out that you get something undefined. So if, for example, it turned out that one of these things was between 0 and 1, then when I went to take the natural log of x minus 1, then I would in fact get something undefined, and so I would not have a solution to this equation. Okay. And so you probably encountered this around sometime in pre-calculus where you started talking about what in pre-calculus context is usually called extraneous solutions. Okay. And so when you're solving an equation, the logic you're using is actually backwards. And so really, unless you have a good reason to be certain that the solution you get is going to work, then once you get the solution, you have to check that it's actually a solution. Because what you're really proving is if there's a solution, it's one of these things that I got out of my solutions, but then those things might or might not actually end up being solutions at the end of the day. I did also want to point out we're going to be writing down a lot of things of this sort over the coming week or 2 weeks or whatever, where we're dealing with elements of R cross R and plugging them into things that look like this. And I wanted to point out, just in case you've had linear algebra, that this x minus 2y, comma 2x minus y business, this thing is actually the kind of thing that you talked about a great deal in linear algebra, if you've taken that before. If not, you'll get to do it next. And this is actually the matrix 1 minus 2, 2 minus 1, times the vector x, y. So this is if you've had 240. I mean, it's still true if you haven't had 240, but you can just ignore what I'm saying if you haven't had 240. And so really what this is asking, ultimately at the end of the day, is, hey, is there a solution to this system of linear equations, which if you've taken linear algebra ends up being some question about some determinant of some matrix? And so in linear algebra, you delve sort of deep into the theory of these so that you can, rather than thinking about this kind of thing every time, do it in a very systematic way. Again, certainly you don't need to know anything about matrices, and I'm probably never going to talk about matrices again for purposes of this class. But I just wanted to note that when I'm talking about these kinds of functions from R cross R to R cross R, then really I'm talking about the sorts of things that come from matrices in linear algebra. And so you will see it again if you take 240 after this in a different guise. Okay. Last up, I wanted to give you an example of this sort like the one with the big xi. So I went ahead and just said define zeta of S. This is going to be the set of ordered pairs A, B in the power set of some set S cross the power set of S, such that, and then the condition I want is A is a subset of B. Okay, so first part, prove that this is infinite. Second part, okay, so here are two parts on the infinite side and the finite side. Very akin to the question like this on the homework, which I think is 56. Yes, 56. So this is very much in the spirit of 56. So I'm going to give you a few minutes to think about this, and then we'll talk through both of these and make sure that we know what's going on so that hopefully you feel very prepared to think about 56. Okay, so let's talk about these. So probably the most important skill in all of these questions is learning to parse what the definition is telling you. So in this case, if I start with a set S, what is the thing I'm getting as zeta of S? This thing I'm getting as zeta of S is the set of ordered pairs of subsets of S, where the first is a subset of the second. Okay. So just as an example, one element of zeta of z plus would be something like the ordered pair 1, 3, 7, comma, and then the set 1, 2, 3, 4, 5, 6, 7. So that is one element. Are we on board with what this set is? Okay. In order to prove that zeta of z plus is infinite, I need to give you a non-terminating, non-repeating list of elements of zeta of z plus. Can someone tell me how to make such a list? Yeah, that sounds great. So I'm going to make a list, and in my list, I'm always going to put 1, or rather, I'm always going to put the set 1 as the first slot. And then for the second slot, I'll start with the set 1, 2. And then I'll move on to the set 1, 2, 3. And then the set 1, 2, 3, 4. And so on down the line. So just to be clear, the nth term here will be the set 1, comma, the set 1, 2, up to n. And this is definitely a non-terminating, non-repeating list of elements of zeta of z plus. Thanks, May. Okay. The other half of the question, the finite half, was about what happens if F is a finite set. Or S. I think I said F. Prove that if S is finite, and let's just go ahead and say its size is n, then the size of zeta of S is at least as large as 2 to the n. And now I think this question has the potential to be a bit tricky, although I think you get a huge hint if you psychoanalyze the question. And by that I mean there's this 2 to the n here in the question. I'm talking about subsets. Where have I seen this 2 to the n before? It's the cardinality of the power set, right? So this is really the key observation here, is that this thing is the size of the power set. Okay. So that sort of gives us an idea of how we're going to try and prove this. So namely, how do you show a set has at least 2 to the n elements? Well, you write down 2 to the n different elements. And in this case, since the power set has 2 to the n different elements, what we're going to do here is we're going to write down one element of zeta of S for every element of the power set of S. Okay, and then since the elements are going to be visibly different, that will prove our result. Okay, so does anyone have any idea for a particular element of the power set of S, what pair I'm going to write down? So I definitely want to pick A to be one of the slots, which I'm allowed to do because A is an element of the power set of S. what can I definitely write here in the second slot to make sure this is true? Alex has a different way of doing this. Alex has suggested the empty set A, which definitely works. The empty set is a subset of every set, so in particular, the empty set's definitely a subset of A. So if for every A in the power set of S, we wrote down this set, that would be 2 to the n different sets, and we'd be done. Okay. So this gives us a proof. There are a few different ways we can do it. So this one, that's great. Another is to write down A comma A. A is always a subset of itself, so that will give me 2 to the n different elements, and so that will complete the proof. Or A is always, in fact, a subset of S, so we could write down A comma S, and that will always work. And so I think any of these 4 things will give us 2 to the n different elements of zeta of S, and that will show us that the size of zeta to the S is always at least 2 to the n. So any one of these 4 things will work. All right, any last questions about that? Alrighty, well with that, have a good afternoon. I'll hang around for office hours, so if you have some more questions, go ahead and just drop them into the chat and I will be happy to talk about them. And if not, I'll see you tomorrow afternoon for office hours, which remember are not in the morning, but in the evening, but in the afternoon tomorrow. Or if not, then I'll see you on Wednesday. Have a wonderful afternoon.